Okay, so this is a continuation of the topic that we were discussing on correcting influence of variability. And today we're going to be focusing on three different things, the cycle time, performance and variability, and the diagnostics and improvement. So we're going to close this topic by looking at some of the expressions that we define, and we can, by looking at those equations, we're going to start deciding, okay, so if our goal is to do this, then we should try to do this and that. Okay, so that's going to be the last part of this lecture. But before we get into that, we need to talk a little bit about the cycle time. And so far, we have considered issues of utilization, of the machines, the variability of the processes happening on those machines, and also the last lecture look at the batching of the parts and how that translate into the cycle time. So we now move to a more complicated performance measure, which is the cycle time. And cycle time is going to show up, I would say, always when you're trying to analyze the performance of a system. Actually, any manufacturing system, you want to make sure that you can produce what you're supposed to produce in the most efficient way, but at the same time, that is, you can reduce the cycle time as much as possible, because having a small cycle time means that you can produce more. Okay, but at the same time, you need to have that balance of having an efficient process, a high quality product, by also having a cycle time that allow you to be very productive. So first we consider the cycle time at a single station. And later we will describe how this station cycle time combines to form the cycle time for a line. Okay, so on the next slide, I have a very general definition of what cycle time is. So the average cycle time at a station is made out of the following components. So you need to consider all these components to be able to estimate that cycle time. So it includes the move time of those parts, the queue time, the setup of your machines, the process time, the time that the parts are waiting in batch, or the time that they're waiting to complete a batch, and wait to match time. Basically, if you need to combine two components, maybe you need to wait until the other process is finished so you can combine those components coming from your line. Okay, so it involves a lot of things. You're listing 7 here, but it's likely you can have, like, if your process is depending on an operator, that can also influence your cycle time. In terms of assembly operations, assemblies complicate flows in production systems because they involve matching. And this is what I was referring to a minute ago. So in a matching operation, processing cannot start until all the necessary components are present. So if you, for example, if you're assembling, I don't know, a cell phone, well, maybe you need to wait until the screen shows up, and you need the components and also the battery. So in order to get the whole thing together, you might need to wait for some of those components to show up. Okay, so the assembly operations law, the performance of an assembly station is degraded by increasing any of the following. So the number of components being assembled is number 1. the variability of the components arrivals and finally the lack of coordination between component arrivals. Okay, the more components you have, most likely the more you're going to have to wait to get the whole thing together. Variability of component arrivals and the lack of coordination kind of related. Both of them are going to avoid the arrival of the parts at the required time. So a lack of coordination between component arrivals, meaning that sometimes you're going to have to produce a sub-assembly in order to put it into your final assembly. So that could be part of your process, but sometimes you are buying a component, so that's not necessarily part of your process. So if your supplier is not delivering your components on time, that most likely is going to affect your final assembly. Okay, so there's a lot of things that can happen. So some observations, this law can be viewed as a special case or a special instance of the variability law. So the number of components affected by product and process design, the arrival variability affected by the process variability and the production control, and coordination affected by scheduling and shop floor control. Okay, so on the next slide, it's basically a repetition of what I mentioned earlier, but now I'm putting that into an equation. So basically, the cycle time is the addition of all these components. Okay, so the date times typically make up for 90% of the cycle time. So that means that you're actually spending only 10% of the time on the actual added value to that component. The rest is basically waste. Okay? And you know a little bit about the lean theory or lean manufacturing theory. What you try to do is to eliminate that 90% of the time, try to reduce that as much as possible so you can have more added value processes into your component or part. So in terms of the definition of the line cycle time, the sum of the cycle times at the individual stations less any time that overlaps two or more stations. Okay, so when you start looking at the total cycle time for your part, you're basically looking at the cycle time for going from one machine to the other to complete the sequence. In order to compute that cycle time, you need to take into account that there will be some overlapping between the processes, especially if you're doing multiple parts. Okay, because maybe when you're processing part 1 in the first machine, or maybe when you're processing part 5 on the first machine, you're already doing part 2 on the second machine, and you're doing part 1 on the third machine. So I'm going to show you an example of what I meant by that in a second, but what I'm going to explain is related to this. So we need to take into consideration that the cycle time, you have to take out any overlapping time between stations. Okay, so here's the example. To illustrate the effect of the overlapping cycle times, we consider a 3-station line with no variability in demand or process. So we are making everything very simple in order to illustrate this point. So we have a setup time for each one of the stations, and we have a unit processing time for each one of the stations from 1 to 3. Jobs arrive deterministically, so again, no variability. We know the arrival time for each one of the parts, and we have batches of 6 every 35 hours. A setup is done for each batch, after which jobs are processed one at a time and are sent to the next station. And the utilization of the stations are 49%, 75%, and 100% respectively. So for station 1 through 3. So using the expression for cycle time split, meaning that we are considering batches of 1, we can compute the cycle time for the first station. So CT1 is going to be equal to CTQ plus the setup for the first machine plus K plus 1 divided by 2 times the processing time of that first station. So for this first station, that's going to be time in the queue 0. The setup time is 5. And we have batches of 6. So 6 plus 1 divided by 2 times the processing time for that first station. This is going to be equal to 12. And the queue time is 0 because there's no variability in the system. Okay, so that's why I'm using 0. So let me put that here. Queue time is 0 because there is no variability in the system. So we can estimate cycle time for second station and the third station in a similar way. So we have CT2 going to be equal to CTQ plus the setup of the second machine plus K plus 1 divided by 2 times the time or the processing time for the second station. And this is 0 plus 8 plus 6 plus 1 divided by 2 times 3. So this is 18.5. And then for CT3, CTQ plus S3 plus K plus 1 divided by 2 times T of 3. This is 0 plus 11 plus 6 plus 1 divided by 2 times 4. This is 25. Okay, and sometimes you get these numbers, you will think that adding these 3 components will give you the total cycle time for the manufacturing line. So for example, doing this, so CT will be equal to CT1 plus CT2 plus CT3, which in this case will be 12 plus 18.5 plus 25, which is 55.5. But what happens here is that you're not considering any of the overlapping components of the cycle time. So for example, when you're performing you're not performing that setup for each part, for example. So when you're performing that setup, you can have other parts running on the other machine. Okay, so what I mean is, this computation right here is not correct because it's not taking into consideration, or it is ignoring the overlapping. Okay, so in order to show you the right way to compute this cycle time, we have to look at the next slide. I think a picture explains or can help explain this specific problem. So here's what's happening. We have batches of 6, right? So we start by working on station 1. So we have the setup for the first part, and then we start processing the first part, the second part, until the 6th part, right? But as soon as you're done with the first part, you can send that one to the second machine. Okay? So that means that you can start that setup for the second machine after the first part is completed. Okay, so you start the setup and then you start processing the next 6 parts. And then when you're done with the first part of the second machine, you start the setup and then you move to completing the process. Okay, so the cycle time for the first job actually is not the 55 units. That will be the cycle time for processing all the parts. The cycle time for the parts actually is the average of each one of the cycle times individually. So for example, you have the cycle time of the first part that is going to be this line right here, 33. Then you can compute the cycle time of the second one. That will be 37. The cycle time of the third one, 41, and so on. So at the end, by considering the overlapping of the processes, we can come up with the average for the cycle time of the parts. Okay, so for this deterministic example, we can compute the cycle time by following the jobs in a batch one at a time through the station. The first job finishes after 33 hours, the second one after 37, and after that you increase by 4 every time. So the average cycle time is the average of these numbers, 43, which is significantly less than 55.5. Okay, so the way we're computing this is we are doing 33 plus 37 plus 41 plus 45 plus 49 plus 53 divided by 6. And that is giving you this 43, which is going to be less than what we computed initially, 55.5, which is not correct. Okay, so you see the idea. When you're computing the cycle time, you need to take into account, or the cycle time of the parts, you need to take into account that there will be some overlapping between these processes. Thus, one must not use equation or this equation to compute the cycle time for any timeline. Okay, that's the other point. Okay, so that basically summarizes the idea of the cycle time and the point that I wanted to illustrate in that sense. On the next part of the lecture, basically what I want to do is to talk a little bit about diagnostics and improvement. So again, we have mentioned already that attacking variability can help in improving the performance of your system. We already mentioned that attacking that variability earlier in the process is better, because if you can improve the variability at the beginning of the line, then the spread of that variability is going to be reduced. So the objective is to increase the throughput, reduce the cycle time, and improve customer service. The levers is reduce variability directly, buffer using inventory, buffer using capacity, buffer using time, and increase your buffer flexibility. So we have mentioned those points already in class. So in terms of increasing the throughput of your system or the throughput of a line, that is going to be given by the first equation. So this is throughput is going to be equal to the bottleneck utilization times the bottleneck rate. So basic checklist of policies for increasing throughput is as follows. So increase the bottleneck rate by increasing by increasing the effective rate of the bottleneck, and this can be done through equipment additions, staff additions, or training, covering stations through breaks or lunches, use flexible labor, quality improvement, product design change to reduce the time at the bottleneck, and so forth. So there's a list of things that you can do to make sure that you can increase your throughput through increasing the effective rate of the bottleneck. Another thing that we can do is increase the bottleneck utilization by reducing the blocking and starving of the bottleneck. And there are two basic ways to do this: buffer the bottleneck with width, or buffer the bottleneck with extra capacity by adding more machines probably, or some operators. So this is basically the idea. So throughput is going to be related to the probability of the bottleneck being busy and the bottleneck rate. So in order to improve or increase the throughput, you can reduce the blocking or the starving, which is connected to this part of the expression. Buffer with inventory, reduce the system desired queue. So this can be connected with the cycle time of the queue, which is linked to one of these three things, or all these three things. So in order to make that happen, you can reduce the variability and also reduce the utilization. If you focus on the second part of that equation, then you want to increase the capacity by adding equipment, increasing operating time, reliability, or reduce the yield loss or rework. Okay, so the efficiency of the quality of your process must be very high. And the note, if width is limited, then the system degrades via throughput loss rather than width divided by cycle time inflation. So here's a good example. This one is coming from your textbook in order to show you what are the things that we can consider for increasing the throughput. So this is a computer or a company that has printer circuit board plant that contains a line with two stations. The first station is called a resist supply, applies a photoresist materials to circuit boards. The second station is called expose, expose the boards to ultraviolet light to produce a circuit pattern that is later etched on the boards. Because the expose operation must take place in a clean room, the space for WIP between two processes is limited to 10 jobs. Okay, so you're going to have a capacity in terms of your WIP. Capacity calculations show the bottleneck to be exposed, which is the second station, which requires an average of 22 minutes to process a job with a square coefficient of variance of 1. Receipt supply requires 19 minutes per job with a square coefficient of variance of 0.25. In addition, and not included in the above process time, exposure has a mean time to failure of 31 hours and a mean time to repair of, I think these numbers are a little bit off, so let me make a correction here. So the mean time to repair, the mean time of failure is 3 1/3 hours, and the mean time to repair is 10 minutes. While the second station has a mean time to failure of 48 hours and a mean time to repair of 8 hours. Jobs arrive to receipt supply with a fair amount of variability, so we assume that the square coefficient of variance of the arrival process is 1, and the desired throughput rate is 2 jobs per hour. Okay, so this last sentence right here is basically what we want to see in our process. We want to have a throughput rate of 2.4 jobs per hour, and we want to know what things we need to do to get to that point. Okay, so essentially what we have here is a two machine process. We have the receipt supply, and then we have the exposure, which is the bottleneck, and has a capacity limitation of 10 jobs in terms of WIP. And finally, we want to see a throughput of 2.4 jobs an hour. Okay, so the solution that we can think of initially is, okay, so we know our capacity, our bottleneck is the second machine, so we might be able to increase the capacity to an extra 10 jobs. Okay, so the company is thinking of expanding second exposure, so basically adding another machine to increase capacity to 20. But the question is there a better solution than that? Is there any other thing that we can do other than increase the capacity? Because adding this second machine or this second, because this is a clean room, right? So adding another clean room is very expensive. So the question is this the only solution? Adding the second exposure machine to increase the capacity to 20, or can we do other things to increase throughput? So the two principal tools at our disposal are the BUT equation for computing the queue time and the linking equation, which is basically looking at the square coefficient of variance of the departure process from the first machine to the second one. So using this in conjunction with the formulas presented in lecture 2 for the effective square coefficient of variation, we can analyze the reasons why the line is failing to meet the throughput target. So we estimated the waiting time in the queue station to be 645 minutes at the receipt supply and 887 minutes at exposure. when the arrival rate is set to 2.4 jobs per hour. So if we let the arrival process to be equal to our throughput, this is what we are going to observe based on the numbers that we have. Okay, so the average width levels are 25.8 and 35.5 at job stations 1 and 2 respectively. So basically, our current width is 10, and what this is saying is we need 35. Okay, so actually adding the second machine to the second station will not solve the problem. We will not be able to get at this point to that level anyway. So this reveals why the system cannot make 2.4 jobs per hour, even though the utilization of the bottleneck exposed is only 92.4%. With the second machine, the clearing room can only hold 20 jobs, but the model predicts that an average number in queue is 35.5 jobs. Okay, so in order to accommodate that, you will need 4 machines, not 2, and not 1, which is what you have right now. Since the real system cannot allow width in front of the exposure to reach this level, receive supply will occasionally become blocked, idle by a lack of space in downstream buffer to which to send the completed part. So not having that capacity to put items in front of the second machine basically is going to stop the production of the first machine. So the result is that neither station can maintain the utilization necessary to produce these 2.4 parts per hour. Okay? So we conclude that the problem is rooted in the long queue at expose, and by little law, reducing the average queue length is equivalent to reducing the average queue time. So we now consider the queue time at expose more closely. Okay, so CTQ of 2 is going to be equal to CA squared of 2 plus CE squared of 2 divided by 2 times the utilization of 2 divided by 1 minus the utilization of 2 times TE of 2. And for this particular problem, we know this is going to be equal to 3.16 times 12.15 times 23.1 minutes, which is going to be equal to 887 minutes. So the third item, TE2, is the effective processing time at exposure, which is simply the raw processing time divided by the availability. So TE of 2 is equal to the time that it takes to process that part on the second station divided by the availability of that machine. And we know that we can compute that also by looking at the mean time to failure, right? So this is going to be equal to T2 divided by the mean time to failure of 2 divided by MF of 2 plus MR of 2. Okay, so we are basically using the same equations that we learned already to expand and search for what are the causes of the deficiencies or non-efficiency of this process. So this is going to be equal to 22 times 31 divided by 3. I'm sorry, this is 3 times 1/3 hours plus 1/6 divided by 31 over 3, and make sure that it's not clear. Three 1/3 and 3 1/3. And this is going to be equal to 23.1 minutes. Since this is only slightly larger than the raw process time of 22 minutes, there is little room for improvement by increasing the availability. Okay, so the 22 minutes, so the effective time is very close to the 22-minute processing time. So there's very little room for improvement here. So the second term in the expression for CTQ2 is the utilization term, U2 divided by 1 minus U2. Although at first glance of a value of 12.15 may appear large, it corresponds to utilization of 92.4%, which is large but not excessive. Although increasing the capacity of this station will certainly reduce the queue time and queue size, we have already noted that this is an expensive option, because we will need to add another clean room for this facility. So we look to the first term, the variability inflation factor, and recall that moderate variability in arrivals, that is square coefficient of arrival, square coefficient of variance of the arrival process equals 1, and moderate variability in process time, that is the square coefficient of the effective processing time of 2 is equal to 1, result in a value of 1 for this term. Therefore, a value of 3.16 is unambiguously large in any system. So we want to know why this is the case. Okay, so if we go back here, that is the coefficient that we are trying to find out why. Okay, so we look at this one, we know this fixing this part is going to be very expensive, so now we are targeting this part. So we want to know why this number is so high, because of this part right here. Okay, so why this occurs, we break it down into its constituent parts, which reveals that the coefficient of coefficient of variance of the effective processing time is equal to 1.04, which is close to what we expect, but the coefficient of the variance of the arrival process of the second machine is 5.27, which is very large when compared to what we are expecting. So obviously the arrival process is the dominant source of variability for this system. So recall that CA square of 2 will be equal to the square coefficient of variance of the departure process of the first machine. Okay, because that's what's going from the first machine to the second machine. We know that CD square of 1 can be computed by using this expression. Utilization square of 1 times CE square of 1 plus 1 minus utilization square of 1 times the square coefficient of variance of 1. And this is going to be equal to 0.88 7 squared times 6.437 plus 1 plus 1 minus, I'm sorry, 1 minus 0.887 squared times 1. And as I show you on the previous slide, this is going to be equal to 5.27. Okay, but the idea here is to see when we compute this thing, where is the largest amount of that number coming from when you look at this and split these parts of the equation. So the component that makes CD1 or CD squared 1 large is CE squared 1, the effective square coefficient of variance of the resist applied machine. This coefficient is in turn made up of two components, a natural square coefficient of variance and ZO21, which is an inflation term due to the machine failures. Okay, so we break down CE squared 2 of 1 as follows. So this is going to be A1 MF of 1 divided by MF of 1 plus the mean time to failure or to repair, sorry, mean time to repair of 1. And we know those numbers. This is 48 divided by 48 plus 8. This is 0.8571. The TE of that first machine is going to be equal to T of 1 divided by the availability of 1. So this is 19 divided by 0.8571. So this is 22.17 minutes. Then the square coefficient of variance of the effective process is going to be equal to, and this is for 1, it's going to be equal to CO squared of 1 plus 2 times the mean time to repair of 1 times A1 times 1 minus A1 and this is MR right here divided by T of 1. And this is going to be equal to 0.25 plus 2 times 480 times 0.8571 times 0.1429 divided by 19, and this is equal to 6.44. So by looking at this, line shares of Z squared of 1 is a result of the random outage of the first machine. So this suggests that an alternative to increasing the capacity of exposure to improve the breakdown situation is increasing, an alternative to increase the capacity to the second machine will be to improve the breakdown situation at the first machine. It is important to note that resist supply is the problem, even though exposure is the bottleneck. Okay, so the problem is the first machine, even though we have identified the second machine as the bottleneck. Because variability propagates throughout the line, the congestion problem at one station might actually be the result of a variability problem at the opposite station. And we have mentioned this already. Okay, so by improving the outage problem at the first machine, we should be able to improve the overall performance of the system or the manufacturing line without having to increase, maybe we would need still to increase the capacity, but not as much as right now. So he's saying that we need a 35.5 capacity in order to target that throughput rate. But if we fix the problem at the first machine, we might end up seeing that we don't need to increase the capacity of the second machine, or we need just to increase, but not as much. Okay, so it's a very powerful analysis, and it is using all the equations that we have learned so far. So various practical options may be available for mitigating the outage problem at receive supply. For instance, the company could attempt to reduce the mean time to repair by holding field-ready spares for parts subject to failures, or they could perform more frequent preventive maintenance. So instead of waiting for the machine to fail, they can go every, I don't know, every break, every shift. At the end of each shift, they can go and perform preventive maintenance on those machines. Okay, so I think I'm going to stop here. We are not going to be able to go through the whole lecture because I need to talk a little bit about the exam.